Alright, so let's look at the last page here of chapter 10. We're going to talk about organometallic reagents reacting with acid chlorides and with esters. So let's talk about first what acid chlorides are. I know it's something that we don't usually talk about much until we get to this chapter in first semester. So let's talk about what their structures are. So acid chlorides. So I want to show you a way that we can make acid chlorides, and we're going to kind of look ahead a little bit. So this is a chapter 11 reaction, and we're going to learn what reagents we can use to do oxidations of alcohols. But one thing we can do is turn them into carboxylic acids. So we can take an alcohol and turn it into a carboxylic acid. Again, so that's the next chapter, so don't worry about that right now. And then we can take this and we can add thionyl chloride, again, chapter 11, but the end result here is that it makes this guy, which is an acid chloride. So esters, I think that we've seen those in the beginning when we talked about different functional groups. But esters are like carboxylic acids, except instead of an OH, you have an OR group there. So let's look down below at some of the reactions here, and let's go through some of the bullet points as we do that. So let's take for our acid chloride, let's take this, and to that, I'm sorry, that's a Cl, and to that let's add EtMgBr. So that's the R minus thing, right? So if we're thinking of this in two parts, those are the kind of the parts that you have there. And then we need to use ether as a solvent here. So first step here is that ethyl group comes over and attacks that carbon. What you form is this oxygen here with a minus charge, a chloro group, and then the ethyl would go there then, right? So this thing has a special name. It is called a tetrahedral, because notice it's a tetrahedral and it's an intermediate. So it's called a tetrahedral intermediate. Now there's this electron pressure that you get kind of from oxygen having this negative charge on it. It's having to hold that negative charge up, kind of like a weightlifter would hold weights above their head. And it would really like to reform that carbon-oxygen double bond if it can. So it wants to swing these electrons down. And it's encouraged to do so because we have a pretty good leaving group right here. So what happens is we reform that carbonyl, and then what we get, right, is chloride is lost, and then we're going to get our oxygen and then our ethyl group there. Now, this is not something that can just sit around in solution right now, because that is very reactive. And we have a lot of Grignard reagents around. So this reaction cannot be stopped here. So instead, it continues to react. So we do this again. And that will give us our oxygen, minus charge. But now we're going to have two ethyls on there. And then the last step of this is that we have like an acid workup. So it's a separate step. So this is a workup step here. And what we're going to form here is our ethyls. And then that is going to be protonated to become the hydroxy group. So we get a tertiary alcohol there. Now the same basic thing occurs here down here below when we look at esters. So let's take a look at this guy as an ester. Now the way that we might see this written out in as far as chemical reactions are concerned is you might see like an R, Mg, Br, right, with here's another way of writing diethyl ether. And then your second step would be your acid workup. So then mechanistically, you're coming around here. It's the same thing that we did above, right? So when you look at that, that's the same idea, same principle. So now you're going to have an oxygen with a minus, and now you're going to have an O, CH3, and then an R group down here. And this guy also is your tetrahedral intermediate. Okay? So this actually turns out to be able to leave here too. So I know we've said in the past that strong bases aren't good leaving groups, but we always clarified that by saying that's true for SN2 reactions. So this is not an SN2 step, it's not part of an SN2 reaction, so it's okay for that to leave. One thing we won't kick off is just carbon atoms though. All right, so then if we do that, right, we lose down here CH3O minus, and then we get a ketone with our R group there. And again, this is another thing where you can't stop it here, so we have another R, MgBr. So we come around here, and we do this again. Now that's going to give us O minus with a couple of R's on there. And then the last thing that we do here is that workup step. So add H3O plus. And voila, there we have it. So both of those reactions look kind of similar to each other. And the last reaction in this chapter is actually pretty interesting, and it can be used to make polymers, and that's something that we may have a chance to do a little extra lecture on as we get towards the end of the semester. So let's talk about, first of all, what that is. So what is ethylene oxide? Well, ethylene oxide is made by taking an alkene and adding MCPBA. Do you guys remember that from chapter 8? And what that makes is this ring. So this thing is called an epoxide. So if you've ever heard of epoxide resins, this is kind of one of the functional groups that helps make those glues and polymers. But it's also known as ethylene because it comes from ethylene and oxide to indicate that it's that three-membered ring. So let's take a look at the reaction here. So let's look at something like this. So what if we put a bromo on this? So bromobenzene, and then why don't we make a Grignard out of that? So to do that, we have to have magnesium and ether there. Now, that is going to make this ring with MgBr. Okay? Now, to this, we will add ethylene oxide. And notice here that there's no other carbons there, so this will open up differently depending on the degree of substitution, but it's not something that we see until chapter 14. So then arrow-wise, it's pretty straightforward. We're going to do that, and then we have to break a bond here. So let's see if we can draw out what that product is. So get your ring in there. Okay, so it's a bond here where that little blue dot is. That's where the bond is. And that's going to make a bond to this little green fellow right there, right? So there we have that. Okay. Now, if we want to, we can write that out as a CH2 also. That CH2 is connected to another CH2, which is then connected to that oxygen. An O- there, right? And then the last step of that is your acid workup, right? So that's where you get your ring in there, right? You get your CH2, and then an OH. So a little note on this for the savvy chemist who wants to really master multi-step synthesis is that a couple things are made here. So this, if you were to look backwards, like at what the reactants were, this is where a new carbon-carbon bond was made. Right? That bond right there is new. Remember, it's between those carbons that we outlined before. Adjacent to that, so let's count how many over. 1 carbon, 2 carbons away. So the second carbon having this OH group here, right? And then again, make a note at C2. That usually indicates that you, at some point in time in that synthesis, you use this epoxide, right? So mostly it's a trick for multi-step synthesis, something interesting to put in your toolbox of reactions.